In the final years of World War II, Germany successfully manufactured an aircraft so advanced that it outran everything else in the skies. The Arado Ar 234 Blitz wasn't just fast, it was revolutionary, soaring at a jaw-dropping 540 miles per hour and cementing its place in history as the world's first operational turbojet-powered bomber. Born from a desperate need for high-speed reconnaissance, this engineering marvel pushed the boundaries of technology with a service ceiling of 33,000 feet and the ability to carry 3,300 pounds of bombs. Join us as we uncover the story of the R-234 and ask, could this incredible aircraft have altered the course of history if it had arrived just a little sooner? Revolutionary design features of the R-234 Blitz. The Arado engineering team, led by Professor Walter Bloom, crafted a sophisticated aircraft design that pushed the boundaries of aeronautical engineering in 1941. The R-234 aerodynamic design featured a high wing configuration with smooth, flush-riveted exterior skin that minimized drag. The aircraft's slender fuselage, primarily filled with fuel tanks, contributed to its exceptional speed capabilities of 692 kilometers per hour at 6,000 meters. Furthermore, the wing design incorporated advanced concepts such as tapered symmetrical profiles and optimal wing loading characteristics. The cockpit design of the Arado R-234 represented a groundbreaking step forward in aviation engineering, showcasing innovative features that set it apart from contemporary aircraft. Most notably, the nose section was designed with an all-glass enclosure, offering pilots unparalleled forward visibility, an essential feature for both reconnaissance and bombing missions. The layout of the cockpit was meticulously engineered to enhance functionality and ease of access. Pilots entered the aircraft through a retractable entry step located on the left side, which simplified ground operations. Additionally, a roof-mounted access hatch provided an alternative entry and exit point, further emphasizing the thoughtful design. For rear visibility, the cockpit was equipped with a periscope system, addressing the blind spots typical of aircraft of its time and offering the pilot greater situational awareness. The controls within the cockpit adhered to conventional standards, with familiar throttle and rudder systems that allowed for intuitive operation. However, the R-234 also integrated cutting-edge instrumentation that elevated its precision and effectiveness in combat. Among these was the BZA-1B bomb sight, optimized for dive bombing, and the sophisticated LOTF 7K bomb sight, which worked in conjunction with an autopilot system to enable highly accurate level bombing, bomber and reconnaissance platform. The landing gear design underwent substantial evolution throughout development. Initially, the aircraft utilized a unique trolley and skid system to reduce weight and maximize internal fuel capacity. Subsequently, engineers developed a conventional tricycle landing gear configuration for the production model, featuring single wheels on all assemblies and low-pressure tires for rough field operations. The landing gear system incorporated several innovative features. The nose gear retracted backward, while the main gear retracted inward and forward into the fuselage sides. To address the aircraft's high landing speeds, engineers integrated a drag-chute system, making the R-234 one of the first aircraft equipped with this safety feature. The final design represented a careful balance between performance and practicality. Though the widened fuselage needed for the retractable landing gear resulted in a speed reduction of approximately 30 kilometers per hour, this modification significantly improved the aircraft's operational flexibility and ground handling capabilities. Powerplant engineering breakthroughs. The pioneering Junkers Jumo 004 marked a watershed moment in aviation history as the world's first mass-produced turbojet engine. First of all, this groundbreaking powerplant featured an axial flow compressor design that achieved 78% efficiency in real-world conditions. The engine development, led by Dr. Anselme France, balanced innovation with practicality. The Jumo 004B production model demonstrated remarkable engineering progress, weighing 100 kilograms less than its predecessor. The engine's technical specifications highlighted its remarkable performance and advanced engineering. It was capable of generating a thrust output of 8.9 kilonewtons, delivering substantial power for its size and purpose. Operating at a rotational speed of 8,700 revolutions per minute, the engine achieved an efficient and high-performance output. Additionally, it managed an airflow rate of 21.2 kilograms per second, ensuring a steady and robust supply of air to sustain its operation. With a compression ratio of 3.1, the engine demonstrated a well-balanced design, optimizing power generation and fuel efficiency for the aircraft's demanding requirements. Moreover, the engine incorporated a variable geometry nozzle system and could operate on multiple fuel types, primarily J2 synthetic fuel produced from coal. The integration of Jumo 004 engines into the R234 presented substantial technical hurdles. Primarily, engine reliability emerged as a critical concern, with time between major overhauls ranging from 30 to 50 hours, occasionally dropping to as. The maintenance process for the engine involved several critical tasks to ensure its optimal performance and longevity. Damaged compressor blades, often resulting from foreign object ingestion, needed to be replaced promptly to maintain efficiency and prevent further damage. Turbine blades were regularly inspected for wear or defects, with replacements carried out as necessary. The Riedel two-stroke starter engine required thorough examination to ensure reliable operation. Additionally, the combustor underwent routine maintenance every 20 hours of operation to address wear and tear, ensuring the engine remained in peak working condition. Consequently, the engines demanded extensive maintenance support, with combustors requiring replacement after 200 hours of operation. The pursuit of optimal thrust-to-weight ratios led to experimentation with alternative powerplant configurations. The BMW 003 engine installation, although providing less individual thrust, delivered a 20% increase in speed, reaching 870 kilometers per hour. This improvement stemmed from the BMW 003 lighter weight, which enhanced the aircraft's overall thrust-to-weight ratio. The engine's fuel consumption varied significantly with altitude, consuming 1/3 at 10,000 meters compared to sea-level operations. Ultimately, between 5,000 and 8,000 Jumo 004 engines were manufactured, with production reaching 1,500 units monthly by war's end. The manufacturing process proved relatively efficient, requiring 375 hours per engine compared to 1,004. The R234 cockpit, a pilot's perspective. Inside the sleek fuselage of the R234, pilots encountered a cockpit that merged advanced technology with practical functionality. First of all, the cockpit's position in the aircraft's nose section provided pilots with an unmatched field of view, setting new standards for military aircraft design. The cockpit of the Arado Ar 234 was equipped with a sophisticated array of instruments, reflecting the advanced engineering required for high-speed jet operations. Central to its functionality was the intricate LOT 7K tachometric bomb sight, a highly complex piece of equipment that allowed for precise targeting during bombing missions. This bomb sight, strategically positioned between the pilot's legs, underscored the aircraft's emphasis on accuracy and technological innovation. The instrument panel was meticulously designed to provide the pilot with all necessary controls and information in an efficient and accessible layout. Primary flight instruments were distributed across dual-side panels, ensuring that critical data was always within the pilot's line of sight. Integrated autopilot controls added a layer of operational simplicity, reducing the physical demands on the pilot during long missions and allowing for more precise flight paths. The cockpit also featured a state-of-the-art radio altimeter system, providing accurate altitude readings crucial for low-level flight and bombing accuracy. Advanced navigation equipment complemented these systems, enabling the aircraft to perform effectively in a variety of conditions, from reconnaissance missions to combat operations. This blend of precision instruments and innovative design made the cockpit of the Arado Ar 234 a hallmark of wartime aviation engineering. The bubble canopy design offered pilots exceptional visibility in all directions through clear plexiglass panels. Accordingly, this enhanced visibility proved crucial for both reconnaissance missions and bombing runs. A unique periscope system mounted on the cockpit roof provided rear visibility, primarily intended for defensive purposes. The control system incorporated several innovative features. The pilot operated conventional throttle and rudder pedals, yet the bombing system required unique handling procedures. Before bombing runs, pilots needed to swing the control yoke aside, utilizing the bomb sight control knobs while maintaining visual contact through the optical sight. The cockpit access system reflected the era's engineering limitations. Pilots entered through a roof-mounted hatch, accessing it via a retractable step on the left side and climbing up kick steps. Similarly, the pressurized cabin enhanced pilot comfort at high altitudes. Operational experiences revealed both strengths and limitations. Pilots praised the aircraft's smooth handling characteristics. Nevertheless, the absence of an ejection system posed significant safety concerns, as emergency egress proved challenging under any circumstances. The integration of the patent PDS autopilot system marked a significant advancement, enabling precise control during bombing missions. Furthermore, the periscope sight, derived from German tank designs, facilitated dive bombing operations, albeit with certain limitations in image orientation. The cockpit's design prioritized functionality over comfort, as evidenced by the narrow confines and complex instrument arrangement. In practice, pilots found the aircraft's handling characteristics exceeded expectations, particularly in takeoff and landing operations. Innovative materials and construction. Engineering precision defined the structural framework of the R-234, with its semi-monocoque fuselage design establishing new standards in aircraft construction. The aircraft's all-metal construction incorporated advanced lightweight alloys, primarily focused on reducing overall weight without compromising structural integrity. First of all, the fuselage featured a distinctive flat-top design with stressed metal skin, enabling optimal weight distribution. The empty weight specifications varied across models, with the A variant weighing 9,400 pounds, the B variant at 11,460 pounds, and the C model reaching 13,400 pounds. The wing design of the Arado Ar 234 exemplified innovative engineering, showcasing a two-spar structure that provided both strength and efficiency through meticulous component integration. Each wing section was reinforced with 29 ribs, ensuring structural stability and resilience during high-speed operations. The exterior was covered with metal-stressed skin, a feature that enhanced aerodynamic performance while maintaining durability. The wings were securely attached to the fuselage using a 4-bolt system, which not only simplified assembly, but also ensured a robust connection capable of withstanding the stresses of flight. Additionally, the design incorporated integrated engine mounting points, seamlessly blending propulsion and structural integrity into a unified and highly efficient system. Furthermore, the fuselage design accommodated substantial fuel capacity, with a 1,800-liter tank behind the cockpit and a 2,000-liter tank in the rear section. This configuration enabled an operational range of 1,500 kilometers. The manufacturing process essentially focused on streamlined production methods. The aircraft's exterior featured flush-riveted skin panels, contributing to its aerodynamic efficiency. The production facility at Alt-Lernuitz in Saxony demonstrated remarkable efficiency, completing 200 aircraft by December 1944, with an additional 20 units produced before the war's end. The engine mounting system showcased practical engineering, with each powerplant secured by 3 bolts for efficient maintenance access. Primarily, the structural design allowed for quick component removal and replacement, facilitating field maintenance. The construction process incorporated advanced manufacturing techniques for the time, including specialized methods for integrating the jet engine's high-temperature requirements. The assembly sequence prioritized modular construction, enabling efficient production despite material shortages and manufacturing challenges during wartime conditions. Performance engineering achievements. The technical prowess of the R-234 manifested through exceptional performance metrics that set new standards in military aviation. The aircraft demonstrated remarkable capabilities across multiple operational parameters. The R-234 velocity specifications varied based on mission configuration and altitude. At 5,000 meters, the aircraft achieved 672 kilometers per hour while carrying its maximum bomb load. Without a payload, the speed increased substantially, reaching 740 kilometers per hour. The operational ceiling extended to 10,000 meters, hence providing tactical advantages against Allied interceptors. The aircraft's speed superiority became apparent through operational results. The R-234 outpaced Allied fighters by approximately 100 miles per hour, therefore maintaining virtual immunity from interception during reconnaissance missions. This advantage proved crucial for mission success, as demonstrated during the initial combat deployment over Normandy in August 1944. In terms of operational reach, the R-234 carried approximately 2,800 kilograms of fuel. The maximum range extended to 1,630 kilometers, with a 500 kilograms payload. Engineers achieved this through careful fuel management systems and aerodynamic refinements. The operational radius required for combat missions stretched to 1,240 miles, primarily supporting strategic reconnaissance operations. The bomb load configuration demonstrated remarkable versatility. The standard payload options included a single 1,000 kilograms bomb semi-recessed in the fuselage, 2 500 kilograms bombs suspended from engine nacelles, 3 SC-500 bombs for maximum load configuration, BT-1400 torpedo bomb capability, though with limited ground clearance. The maximum bomb load capacity reached 1,500 kilograms, as well as allowing for various mission-specific configurations. The aircraft utilized an advanced bombing system, incorporating an autopilot interface that adjusted flight paths automatically during bombing runs. The Patton PDS 3-axis autopilot, working in conjunction with the LOTF 7K tachometric bomb sight, enhanced precision during attack missions. Operational effectiveness, ultimately, faced certain limitations. The addition of full bomb loads reduced speed performance, requiring careful mission planning. To address takeoff challenges with maximum payloads, the aircraft employed Walter HWK 109-500 liquid propellant rocket engines, providing an additional 1,000 kilogram force of thrust. These rocket assists, mounted under the wings, were jettisoned by parachute after reaching altitude. Technical challenges and solutions. Persistent technical hurdles shaped the operational capabilities of the R-234 throughout its service life. The aircraft faced three primary challenges: engine reliability, fuel system complexities, and maintenance demands. The Jumo 004 engines presented significant operational constraints. Primarily, these powerplants required major overhaul or replacement after merely 10 hours of operation. Engine failures occurred frequently, with flameouts posing a critical safety risk. The situation worsened over time due to unsuitable fuel usage. The engine's restart capabilities had strict limitations. A flamed-out engine could only be restarted below 4,000 meters altitude and at speeds between 400 to 500 kilometers per hour. Beyond these parameters, pilots faced the prospect of single-engine operation or emergency landing. The fuel system design of the Arado Ar 234 embodied the intricate demands of jet propulsion technology, requiring careful consideration of varying fuel qualities and fluctuating consumption rates. These challenges were exacerbated by the deteriorating war situation, which led to severe fuel shortages and directly impacted the aircraft's operational readiness. To address these pressing issues, the engineering team implemented a series of innovative solutions. Sophisticated fuel management systems were introduced to optimize performance under different conditions, while specialized ignition systems were integrated to enhance reliability and adaptability. Protocols for monitoring fuel quality were developed to detect and mitigate inconsistencies, ensuring the aircraft could operate effectively even with suboptimal resources. Additionally, advanced fuel filtration systems were installed to protect the engine from impurities, maintaining both its durability and efficiency despite the constraints of wartime scarcity. The maintenance demands of the Arado Ar 234 were extensive and required significant time and effort from ground crews, who faced numerous challenges in keeping the aircraft operational. Engine maintenance was particularly demanding, necessitating a complete overhaul every 10 to 25 hours of operation to ensure peak performance and reliability. Damaged compressor blades, often caused by foreign object ingestion, required frequent replacement, while turbine components underwent regular inspections to identify wear or potential failures. Additionally, the combustor required routine maintenance every 20 hours, adding to the already substantial workload. The maintenance burden intensified as the war progressed. Eventually, ground crews developed more efficient procedures, reducing engine replacement time. Simultaneously, parts shortages and Allied bombing of production facilities hampered maintenance efforts. The aircraft's complex systems required specialized maintenance protocols. Undeniably, the introduction of jet technology demanded new maintenance approaches and skills from ground crews. By April 1945, these challenges had taken their toll, with only 38 R-234 aircraft remaining in operational service. Henceforth, the technical challenges faced by the R-234 provided valuable lessons for future jet aircraft development. The experience gained in managing engine reliability, fuel system design, and maintenance requirements influenced post-war jet aircraft engineering practices. These challenges presently serve as historical benchmarks in the evolution of jet aircraft technology. Combat systems integration. Combat systems aboard the R-234 Blitz represented a blend of offensive and defensive capabilities. each carefully integrated to support diverse mission profiles. The R-234 bombing system showcased impressive versatility in its ability to deploy a range of weaponry. The aircraft primarily carried its ordnance on external racks, with a maximum payload capacity of 1,500 kilograms. Its standard configuration allowed for various load combinations to suit different mission needs. This included a single 1,000-kilogram bomb semi-recessed beneath the fuselage for streamlined aerodynamics, twin 500-kilogram bombs suspended from the engine nacelles, and the option to carry 3 SC-500 bombs, providing maximum strike capability for more devastating attacks. The bombing computer system incorporated advanced features for its era. The pilot engaged an autopilot system interfaced directly with the bomb site, automatically adjusting the aircraft's flight path for precise weapon delivery. This integration enhanced accuracy, especially during high-speed bombing runs. The R-234B2's defensive armament consisted of twin 20mm MG-151 machine guns mounted horizontally in the rear fuselage section. Each weapon received 200 rounds from a magazine positioned above the gun mount. The General der Kampfflieger initially mandated this defensive arrangement, yet operational experience prompted a reassessment. The defensive system's effectiveness faced practical limitations. Given the aircraft's high speed, many pilots opted to remove the rear weapons, recognizing that the unnecessary weight reduced performance. The absence of direct rear visibility necessitated the use of an RF-2C periscope for weapon aiming. The navigation suite incorporated sophisticated systems for both reconnaissance and combat missions. The Fuji-218 Neptune VHF band radar equipped specialized night fighter variants, designated as R-234B2 and Nachtigall. This radar system utilized a modified Hurst UA-8 dipole element antenna configuration. Advanced radar installations underwent extensive testing at Erprobungsstelle Werneuchen. The centimetric radar systems featured compact antennas, enabling cleaner installations than previous designs. The research focused on multiple mounting configurations: nose installations for primary target acquisition, ventral positioning for enhanced coverage, and dorsal mounting for aerial target tracking. The Fuji-240 Berlin N1A radar system, intended for the R-234C3 variant, offered target tracking capabilities up to 45 kilometers. Some variants carried additional electronic warfare equipment, including the Fuji-350 Naxos passive receiver system. Operational effectiveness manifested during the aircraft's first combat mission in August 1944. The reconnaissance sortie over Allied positions in Normandy yielded more valuable intelligence in a single 2-hour flight than previous efforts had gathered in 2 months. The combination of high speed and advanced navigation systems enabled the R-234 to maintain virtual immunity from interception throughout most of its operational career. Engineering legacy and impact. The R-234 pioneering design and engineering solutions left an indelible mark on aviation history, establishing benchmarks that influenced jet aircraft development for decades to come. First of all, as the world's first operational jet bomber, it demonstrated the practical viability of jet propulsion in military aircraft. The R-234 aerodynamic configuration, primarily its clean lines and engine placement, influenced post-war jet bomber designs. Indeed, the aircraft's advanced features shaped the development of subsequent military jets, including the English Electric Canberra and Boeing B-47 Stratojet. The concept of laminar flow wings and wing sweep, first tested on the R-234 by February 1945, became The aircraft's engine integration solutions proved particularly influential. Rather than merely adapting existing airframe designs to jet propulsion, the R-234 showcased a purpose-built approach that optimized aerodynamic efficiency. The resulting plan, designated E-370, demonstrated how to combine new technologies with conventional aircraft concepts. The Arado R-234 played a pivotal role as a test platform for several technological innovations that would later become industry standards in aviation. One of its key advancements was the introduction of an advanced pressurized cockpit design, which improved pilot comfort and operational efficiency at high altitudes. The aircraft also incorporated rocket-assisted takeoff systems, enabling it to achieve quicker launches in challenging conditions. Furthermore, specialized maintenance procedures were developed for the aircraft, setting a new benchmark for aircraft upkeep in wartime settings. In addition, the R-234 pioneered high-speed landing techniques, optimizing its ability to land safely even after high-velocity flights, thus influencing future aircraft design and operations. The manufacturing process itself represented a significant achievement. In an extraordinary demonstration of engineering efficiency, the first R-234 V1 progressed from drawing board to rollout in just 15 months. Soon afterward, the production facility at Alt-Lernuitz achieved remarkable efficiency, completing 200 aircraft by December 1944. Operational experience with the R-234 provided valuable insights into jet aircraft development and deployment. The aircraft's performance capabilities proved impressive by contemporary standards, considering the limited expertise about jet engines at the time. Still, several critical lessons emerged from its service. The engine reliability challenges highlighted the importance of robust powerplant development. The Jumo 004 technical problems could have been addressed earlier, potentially allowing hundreds of R-234 beachheads to enter service sooner. This experience influenced future jet engine development programs, emphasizing the need for extensive testing before operational deployment. Manufacturing efficiency improved significantly throughout production. The Jumo 004 engine assembly process required 375 hours per unit, rather than the 1,400 hours needed for contemporary piston engines. Primarily, this achievement demonstrated the potential for streamlined jet engine production. The aircraft's combat performance offered important insights. During its first reconnaissance mission over the Normandy beachhead, a single 2-hour flight gathered more valuable intelligence than previous efforts had collected in 2 months. However, the absence of an ejection system and limited defensive capabilities underscored the need for better crew protection in high-speed aircraft. The technical challenges faced by the R-234 provided valuable lessons for future jet aircraft development. Generally, the experience gained in managing engine reliability, fuel system design, and maintenance requirements influenced post-war jet aircraft engineering practices. The Army Air Force spent considerable time studying both the strengths and weaknesses of these aircraft, incorporating these lessons into early American jet designs. The aerodynamic aspects of the R-234 particularly influenced the development of the F-86 Sabre and other early American jet aircraft. Lastly, while the R-234 arrived too late to significantly impact World War II outcome, its technical achievements and operational experience provided valuable insights that shaped the future of military aviation. The Arado R-234 Blitz remains a symbol of wartime engineering innovation, achieving several aviation firsts. With its groundbreaking design and powerful propulsion system, it reached speeds of 540 miles per hour, and carried impressive payloads. Despite challenges with engine reliability and maintenance, the aircraft's advancements influenced future jet aircraft, such as the English Electric Canberra and Boeing B-47 Stratojet. The lessons learned from its development laid the foundation for modern aviation technology. The R-234 was more than just a bomber. It marked a turning point in the jet age, setting new standards in aviation. What do you think? Could the R-234 have changed the outcome of World War II if it had been deployed in greater numbers? Share your thoughts in the comments below. Thank you for watching.